Okay, this is the SNARS monthly meeting presentation for April 1st, 2023. Our speaker is Dr. Scott McIntosh. He's not here in person, but he put together a custom 30-minute video. He probably, in my opinion, and one of the other members, Derek at W7DLZ, he may be the foremost authority. Maybe authority is not the right word, practical person in the world about propagation solar cycles. So it will be really, really interesting. So let me start the video. And actually would help if I did this.
And good morning, everyone. This is Scott McIntosh. I am the Deputy Director of the National Center for Atmospheric Research in Boulder, Colorado, and it's my pleasure to talk to you about Sunspot Cycle 25 and its progress towards maximum. And moving on to why we're here. So what and who cares? Well, there's been a lot of discussion about Sunspot Cycle 25 and how big it was going to be. And to cut a very long story short, back in the spring of 2019 in my building, a group of peers met to discuss what Cycle 25 was going to look like, just like the previous two Sunspot cycles. So almost once every decade, a group of experts would get together and consider the state of the art of understanding, plus statistical models and all kinds of other things, in order to understand what the future held and prognosticate to see what was going on. So as a result of that deliberation, the blue curve arose for Cycle 25. In other words, what that means is that the primary or the consensus forecast for Cycle 25 was something that peaked in the middle of 2025, but also was almost of equivalent amplitude to Sunspot Cycle 24, maybe a wee bit less. And that is lower than the historical average, which is shown in green. And for reference sake, right about the same time, a group of colleagues and I made a little bit of a discovery, and I'm going to walk you through some of that in the slides to follow that led to the red curve. And so it's, as you can see, it's somewhat different to the blue curve, and this presented an opportunity to try and understand better what's going on with the sun, because clearly if those two models aren't necessarily the same, and such a massive differential would indicate that maybe there's a problem in our understanding. So all the other thing I'm going to come back to later on as a method of validation is to show you a forecast of the 10.7 centimeter solar radial flux, right? So I'm not going to get into a lot of details of how this was constructed, because that would take up an hour on its own. But basically what I'm showing here is an envelope of the sun's 10.7 centimeter radial flux that we estimated based on a statistical analysis depending on an event that we showed called the terminator. And I'll get into this a wee bit later, but I wanted to show you the metric before we start to add contemporary data to it. So the forecast, of course, is the green line with variance of the light green envelope around it. So you can see there just some sample daily data in red and monthly data in blue. So the big challenge on our hands is to try and understand the sun's internal magnetic energy engine. Okay, the sun's internal magnetic field dictates the time and location that magnetic field erupts through the sun's surface to make things like sunspots. We're going to make the assumption that this process is a buoyant one. In other words, that the magnetic field is more buoyant than its surroundings, kind of like a hot air balloon, and bubbles up and ruptures through the sun's surface, and we see it as a collection of positive and negative polarity things. This beautiful animation that covers some 3 decades of evolution illustrates the yellow and blue as being positive and negative polarities, And the other assumption we're going to make is that what we see on the sun's surface is literally the tip of the iceberg. And unfortunately, it seems like that tip of the iceberg may have misled a lot of my peers. So moving to my own investigations. Back in 2002, I was a postdoctoral research fellow in the basement of Building 26 at Goddard Space Flight Center, working on the SOHO project. And my supervisor at the time told me that I should go look at these things called EUV bright points. They're so called because they appear in EUV images of the sun, of its corona, and they're bright. So the image on the left shows you the sun at about 1.5 million degrees Kelvin, and you can see that the sun is pockmarked with these small, bright intensity concentrations. Funnily enough, they're called bright points. My boss at the time said you should identify them and track them. You never know, you might find something very interesting. So I developed a numerical algorithm that went into those images and identified all these little bright concentrations, and the result is shown on the right-hand side. Now, when you look at these over a long period of time, and I started this calculation, like I said, in 2002, by the time late 2011 and 2012 was appearing, there was a pattern starting to develop. And, in the middle of 2012, there was a little bit of an epiphany occurred with me when I was looking at the path of these EUV bright points as a function of latitude and time in context with the sunspot cycle. And one of the first things you'll notice from panel C there is that there's significant signal in the EUV bright points between, say, 2009 and 2011, where there seems to be 4 distinct bands of things concentrated around the sun's equator. And this is identically the time when the sun cannot make any sunspots or solar minimum. So I've annotated these old charts, right? These go back to all the way to 2012. The other thing we noticed was that the low latitude bands, the 2 nearest to the equator, have a definitive end. And at the very same time as that end, sunspot activity seemed to spring to life at mid-latitudes. Now, one of the things that was kind of interesting and very helpful was that the very profound hemispheric asymmetry in cycle 23 created an opportunity for us to see what was going on. And by that, I mean the fact that the northern and southern hemispheric sunspot numbers were out of sync by almost 2 years. One thing we also noticed was that the bands of EUV bright points progressed quite linearly. And so we kind of made an inference that the overlap and interplay of those bands helped to shape at least the landmarks of the sunspot cycle. And in this case, how it came out of solar minimum, but maybe also how it went into solar minimum. So the hypothesis stepped forward a wee bit further. And, based on our ability to draw straight lines, we made a prognostication back in 2012, because we also identified that the high latitude behavior of these bands starting at 55 degrees was very regular. In other words, every 22 years, every 11 years or so, a new set of bands started at 55 degrees and took something like 17 years to migrate towards the equator. And even though we had a meager 16 years of data, you could see this system setting itself up. So back in 2012, our guess was that the activity on those bands would continue to follow the lines. And so we sketched out 2 sets of lines, the red dashed lines and the magenta lines. The red dashed lines were the continuation of sunspot cycle 24, and the purple or magenta dashed lines were where we guessed we would get cycle 25 appearing based on history. The ovals that I show in gray were where we thought that the first spots of cycle 25 would start to appear. This was a kind of ballsy thing to do back in 2012, but how did we do? So if I fast forward to 2017, we wrote a paper announcing that we had seen the first embers of Sunspot cycle 25, and we're still tracking the demise of Sunspot cycle 24 towards the equator. Now, if I were to flip-flop back and forth between those plots, you'd realize that we haven't really changed much, but the sun is largely doing what we expected it to do. Jumping forward again. Okay. There's something underlying that I didn't tell you much about. The sun's sunspot cycle and the progression of sunspots as a function of latitude that are both shown here. And again, I've shown you the hemispheric sunspot number, red for the northern hemisphere, blue for the southern hemisphere, and you can see the very wicked hemispheric asymmetry both in cycle 23, but especially in cycle 24. There's something underlying that, and it's the 22-year magnetic or Hale cycle. I'll show you what that looks like in a second, but colleagues of ours back in the late 80s discovered that this wasn't all of the story, and that indeed there was a thing called the extended solar cycle. And we're going to make a proposal to you that the extended solar cycle really is the 22-year Hale magnetic cycle, and that those Hale magnetic cycles interfere, overlap, and then ultimately shape the sunspot cycle. Just to illustrate that, I've drawn on here, using bright points to help me track features, what a cartoon or a schematic of the Hale cycle evolution looks like. So in this case, I've introduced magnetic polarity, positive polarities in red, negative polarities in blue. You can see polar evolution, you can see sunspots, you can see these curious events at the sun's equator where things seem to switch on and switch off. Even if you pay close attention, you can see the profound hemispheric asymmetries, because that seems to be when the bands of a given magnetic polarity seem to start at 55 degrees latitude on their path towards the equator. If you look at the movie playing on the left-hand side, we've tried to add data and some animation and evolution to that. Also shown on this plot are the large-scale features that track what we call neutral lines, or lines where the magnetic fields cancel in green, and those are prominences or filaments observed in the H-alpha line. Some of you probably look at the sun in H-alpha and you see these dark features on the disk or bright features on the limb. Those are prominences and filaments. They tell a pretty story. So if we go in and look a little bit more at the end of sunspot cycle 24, we're going to introduce this concept of the terminator, or it's the end of a Hale cycle at the equator. So remember, those two bands come in towards the equator and almost appear to annihilate. As they annihilate, activity at mid and high latitudes appears to take off. So not only is the activity a function of latitude, we want to show that activity is also longitudinal. So in other words, that these events, the so-called terminators, also travel around the sun. And so for a very narrow period of time in 2010 to 2014, between the stereo spacecraft and SDO, we could make the first ever 360-degree observations of the sun's corona. And in this case, you can see that the terminator is a longitudinal effect. You pay attention to the panel in the center here, panel B, that looks at what we call a Hofmöller diagram. So each slice vertically through this data set is a ring of data at a given range of latitudes. So the middle one is plus or minus 5 degrees latitude. So I take that, average the signal over that, and each slice steps forward in time. So you can see that there's a dearth of bright points at the equator, which then rapidly spreads in the time scale of a couple of months, completely around the equatorial region. At the same time, in both the northern and southern hemispheres, activity kicks off in the form of these dark bands. So in other words, there's a signal at the sun's equator that then rapidly propagates in longitude. So we're developing a little bit of a hypothesis here. They're basically that these underlying halo magnetic cycles overlap and interact with one another. They have very regular starts at high latitudes, and their migration time to the equator is variable. That's something we're trying to understand. In this puzzle, longitude is very important, and the interaction of the bands towards the equator and with each other is not always the same. However, the neat kind of thing is that they can be tracked using synoptic observation data sets, just like the ones that you guys could build. The largest part of our hypothesis is that the interaction of these halo cycle bands shapes the evolution of sunspot cycles, including their amplitude, one of the missing factors of sunspot cycle prediction. And what we're going to suggest is that if we measure the separation of terminator events, it gives us an idea of how much those halo cycles overlap one another, and try to identify if there's a relationship between the amount of overlap in halo cycles and the eventual sunspot cycle amplitude. So we identified 14 terminator events in the observational archive going back to 1860, but for our colleagues that wasn't enough. They challenged us to develop an algorithm to go back even further and not only verify the terminators that we identified in our analysis, but also to go back further into the furthest part of the observational record, so back into the 1750s, and that's shown on this slide. So the monthly sunspot number is shown in black. A smooth version of that is shown in red. Overlapping, overplotted in that is a blue curve, and that blue curve is a 14-month running average. And you can see in that there's grand minima, especially the Dalton minimum, about 1800, and then other kind of lower minimum, but you see that the amplitude of sunspot cycles varies quite dramatically. If you remove that trend, then you get the second plot. Now, from that second plot, we apply what we call a Hilbert transform. Some of you are probably very familiar with Fourier transforms, but in a situation where the phase of the signal is variable with time, you have to use something a little bit different. And so we use a Hilbert transform because it allows us to decompose the time series into an amplitude function. It's a function of time. So how the amplitude of the signal varies is a function of time, but also how the phase of the signal varies with time. And that's shown in the lower plot. And there's a few things there you'll instantly gleam onto. So in that case, the yellow diamonds are the terminator events, and they coincide with the phase of the Hilbert transform crossing zero. And you'll see quite nicely that we can reproduce the 14 terminator events that are observed directly, but also we can go back and see many, many more. And the other thing you'll notice is if you go back to the 1800 with the Dalton minimum, you'll also notice that when the sunspot cycle amplitudes are very small, those terminator events seem to get quite widely separated. And conversely, when the sunspot cycle amplitudes get compressed, the terminators get a little bit closer together. So I'm going to conduct a little bit of an experiment now. I have 24 individual events measured since 1750, and I'm going to compare the relationship between the terminator separation, delta, and the intermediate sunspot cycle strength and the upcoming sunspot cycle strength, because based on this cartoon, how far that event in 2011 slips to the right or the left, we suppose impacts the amplitude of cycle 24. Okay, so that's our premise. Let's look at the experiment. If I look at the terminator separation for these 24 events versus the intermediate cycle strength, I have no predictability. You can see there that, all it does is yields an average value of the sunspot cycle, and you have nothing to predict. However, if you look at the terminator separation versus the upcoming cycle strength, you get a nice clean relationship. And lo and behold, you would have pretty much almost nailed sunspot cycle 24 amplitude and 23 and many, many others. And just for contrast, I show in magenta, again, the consensus sunspot panel prediction panels forecast of 115 spots in magenta. So you can see what that looks like. Back in the day when this plot was made, we were anticipating, again, using the Hilbert transform, that the terminator of sunspot cycle 24 would occur sometime late in 2020. That didn't materialize. Had it materialized, we would have been one of the top 5 sunspot cycles of all time. That's a little bit of where we're going to go to next. So wrapping up this part of our talk, you can observe the progression of Hale cycles directly. The data seem to support the concept that Hale cycles interact in such a way to modulate the production of sunspots, as manifested through the terminators. Using the key feature of the Hale cycle, their death, we have established a relationship that allows us to estimate the cycle of upcoming sunspot cycles. After much waiting, the terminator of the Hale cycle allows us to finally forecast the cycle 25 amplitude. And that's where I'm going to go next. I'm going to show you that terminator, the one that we were waiting for, in a lot of different facets. Now, should our forecast of sunspot cycle 25 be correct, this is not using the physics, or at least as we interpret it. It's not using the physics that's described in many of the solar physics textbooks, should the forecast be accurate. That means we got to go back and revisit what that is, and maybe it's time to change some perspective. The other thing that's interesting to note about our terminator events is that they provide a strong key time to robustly explore a host of other solar and geomagnetic activity measures, like the F10.7 solar radio flux that I showed you earlier. Okay, so we're going to go into that a little bit and validate. So we had to wait another year, but you can quite clearly see the 2021 terminator event in the data. You can see the massive overlap in the activity bands. It's very clear. You can see the bands of cycle 24, 25 in here. You can see the rapid growth of sunspot cycle 25 following the terminator event. So there's a win. One, we speculated that the terminator event would occur, and as it occurred, sunspot cycle 25 would take off. Showing it in a little bit broader context, here is the last 3 sunspot cycles, the last 3 terminator events, and you can see that they have pretty much the same signature. In fact, this one's our 3rd in the contemporary data set. Pretty stuff. I showed you the end of sunspot cycle 23. End of sunspot cycle 24 is no different. This data is pretty much current, and you can see for yourself that, yep, the signal at the equator kind of petered out, and then boom, all of a sudden it's gone, and there's growth at mid-latitudes. One of the interesting things I'll refer you to also is that there seems to be some kind of change of activity above the activity band, so in that region between 40 and 60 degrees, but I'm not really going to get into that in this talk. Just note that it happened. So there's been a global change in the sun's magnetism as a result of this termination event. One of the nice ways of illustrating this change and the change in evolution, or the comparison between what happened in 2011 and what happened recently, is just to take slices through latitude as a function of time. And you can see from this picture the comparison, what happened at the equator, the massive drop-off in UV bright points. Yes, this event did actually occur. It's very similar and characteristics to the event of 2011. So we can assume that, yeah, it's the same thing. If I look also now at my Hofmöller diagrams, you see the same kind of behavior. In fact, the behavior at the equator is probably even a little bit more profound than it was the last go round a decade ago. So this is covering, for these Hofmöller diagrams cover from 2014 to the present day. And you can see that the Terminator event occurring in late 2011, but there's, 2021. But you can also see that Sunspot Cycle 25 had a couple of false starts. Again, something I don't really have the time to get into today. But you can see that activity of the mid-latitudes on either side in the southern and northern hemispheres really did get going after the Terminator event, and the equatorial activity died. The eagle-eyed people in the audience will note that also in September of 2016, there seems to be a converse event that where activity seemed to kind of die off. And again, it's a subject for another day and another talk. I don't have time to get into it. So, now that the Terminator has officially occurred, we can revise our forecast of Sunspot Cycle 25's amplitude finally. With the December of 2021 Terminator, we can revise the Terminator separation, and what we find is that Sunspot Cycle 25, in this case, would be somewhat equivalent to the mean, so the M. So now you can see our original forecast and the modified forecast in green. You'll notice that both of those are still significantly above the magenta panel prediction. Looking at going back again to consider one of our initial plots, and again this data is contemporary, you'll see that the green daily sunspot data and the monthly black data line up very well with our forecast of Sunspot Cycle 25 amplitude and timing. And in fact, this plot doesn't really fully appreciate the timing, because we actually think that Sunspot Cycle 25 will peak no later than the middle of 2024. So 1 entire year earlier than this plot indicates. I'll get to that in a second. If you want to see it in somewhat higher resolution, here is the data, again, daily data in green, current data in red, monthly data in black, against the consensus forecasts, the original consensus forecast in teal, and then a time-shifted consensus forecast that was done to try and capture the starting evolution of the cycle better. You can see it doesn't make a lot of difference. One of the things that we've learned in the time of undertaking this research is that the polar evolution, or the evolution above 55 degrees latitude, is very important to helping us establish the timing of what the sun's doing. So there's certain key factors that we can track in this. One is the polar magnetic field strength, shown here in the panel B, and the panel down, that's taken from the Wilcox Solar Observatory at Stanford University. And then also the evolution of the sun's magnetic field. Those of you that pay attention to the sun will know that when the sun goes through solar minimum, comes out, it has these things at its poles called polar coronal holes. As the sun's polar reversal process continues, those polar coronal holes close up. As they ultimately close up and the magnetic field reverses, that typically coincides with solar maximum. And so by establishing when those things are going to happen, we can get a better idea of the window for max. The sun's polar coronal holes have largely gone. Here's the analysis that goes up to the current time, and an image just from a couple of days ago. So the polar coronal holes appear to have pretty much closed. Furthermore, when you look at the Wilcox Solar Observatory's polar magnetic field measurements, you see that the polar magnetic fields are back to almost zero. In other words, that reversal process is continuing. Now, if I want to share with you what the contemporary F.7 solar radial flux is doing, There we have this beautiful plot, and usually if I have more time, I walk through several examples of this to show how it builds up. But again, if you recall the start of our presentation, the red data is the daily data, the blue data is the monthly, and it's against a statistical average based on terminators and terminator separations. And you'll see that the data itself is tracking that green envelope rather well, and probably remiss to say that a forecast of this capability or this clarity doesn't exist in our community, but it's very invaluable to people looking at objects in low Earth orbit and other things, because the F10.7 flux is a good proxy for how the Earth's thermosphere changes and affects things like satellite drag in the low Earth environment, etc., etc. So I'm kind of running out of time, and I appreciate your attention. And I know I've skipped over a lot here, but there's only so much you can do in 30 minutes. But what we've covered is basically that the sun has 22-year magnetic Hale cycle. That Hale cycle is directly observable, but the bands of the Hale cycle overlap and interfere with one another. And that seems to give rise to a shaping of the sunspot cycle. The end of a Hale cycle, or the terminator, is a trigger for the next sunspot cycle to grow at mid-latitudes, and it also starts the polar reversal process at 55 degrees. We have no idea why 55 degrees is so important to this puzzle, but it shows up again and again and again in a whole host of diagnostics. The hemispheric maxima of cycle 25 may not be very separated. So in other words, we might get one single peak this time, and the initial growth in both hemispheres has been very balanced. Based on our analysis, we think that sunspot cycle 25 will have its maximum in 2024. So we've probably got at the most 12 months of growth left, and at that time or shortly thereafter, sunspot cycle 26 should become visible at the same time, again at 55 degrees latitude. So we're going to continue to track this, and I've put some URLs on the slides so that you too can track from the benefit of your couch. But one of the things to really point out is that if we're right, we may require some revision to our understanding of how the sun's magnetic field forms in the interior, how this magnetic Hale cycles interact and overlap with one another. And with that, thank you very much.
Okay, thank you, Scott. And Scott, even though he's not here today, he said he was available by email. So let me tell you what it is. If anybody wants to email him, and we'll put it up on the system. Scott McIntosh, SCOTT, MCINTOSH is his name. And his email address is mscott, so it stands for M as in Mike, Scott, at ucar.edu. That's mscott at ucar.edu. Quite fascinating, technical. The original one was about 2 hours, which was way too much. I'm glad he made it shorter. And I think what I took out of it, besides the 22-year termination back and forth, was twofold. Number one is when I looked at the charts, because I got into ham radio in 1973, I kind of make a correlation to when I did things and I put up antennas and things were pretty good. I could see it in those charts. The other is the next couple of years should be tremendous. It's been getting better and better. Okay, so let me end the recording and we'll do the raffle. This completes the presentation for the SNARS monthly meeting on April 1st, 2023. So let me stop the recording.